Hello, my name is Marsalis Swader, and this is my Calc 3 Project 4 presentation. Today I'll be walking through focusing how we transition from Cartesian coordinates to polar coordinates and how those tools let us analyze Maxwell's equations. To start, I have this operation tools page allowing so I can define a polar del operator as del unit vector r times partial derivative with respect to r plus unit vector theta times 1 over r times partial derivative with respect to theta. Unlike Cartesian unit vectors I and j, polar unit vectors r and theta change direction depending on the angle theta, and because of this, their derivatives with respect to theta matter. So the partial derivative of unit vector r with respect to theta equals unit vector theta, and the partial derivative of unit vector theta with respect to theta equals negative unit vector of r. So meanwhile, their derivatives with respect to r are equal to 0. So looking at the first table, the gradient of p, or scalar field p, in Cartesian coordinates equals del p of from x to y, p of x and y. The partial derivative of p with respect to x plus partial derivative of p with respect to y. In polar coordinates, using the chain rule, expansions, and just transforms into del r to theta, del phi r to theta. The partial derivative of p with respect to r plus 1 over r times partial derivative of p with respect to theta. So the next is divergence. For the vector field f equals f plus g. The Cartesian divergence is partial derivative of f with respect to x plus partial derivative of g with respect to x. In polar coordinates, that vector field is written as f equals m times unit vector r plus n over r times unit vector theta. We take the dot product with our polar del operator. And then when we apply that product rule, the theta derivative generates an extra term because r unit vector r changes with angle. So this expands out to give us the final divergence of partial derivative of m over partial derivative of r plus m over r plus 1 over r squared times partial derivative of n partial derivative of theta. All right, and moving on to the curl Cartesian form. It's so del times let me zoom in actually. Del times f of I plus g of j equals the partial derivative of g with respect to x minus the partial derivative of f with respect to y of k. For the polar form, that is just another document of recorded call with my friend. But anyway, sorry, I digress. The polar form of f equals m times unit vector r plus n over r times unit vector theta. We evaluate the cross products. Cancel it. When you take the r derivative, we get a negative n over r squared k term, and from the theta derivative, we get a positive n over r squared k term, and they cancel out, leaving us with 1 over r times partial derivative of n with respect to r minus partial derivative of m with respect to theta k. On to the Laplacian. With divergence of a gradient, and translates from the second partial derivative of p with respect to x plus the second partial derivative of p with respect to y in Cartesian. the second partial derivative of p with respect to r plus 1 over, oh, I keep flipping to that second video, but where was I? 1 over plus 1 over r times partial derivative of p with respect to r plus 1 over r squared times the second partial derivative of p with respect to theta, and polar by substituting m equals partial derivative of p over r with respect to r, and n equals partial derivative of p with respect to theta. So finally, our vector identities, the divergence of a curl and the curl of a gradient, are both equal to 0 because the mixed partial derivatives are equal, as proven by Clairaut's theorem. And for curl of a curl, we use the triple product identity often. Remember, it is BAC-CAB to expand it, which is, to expand it into del operator times dot f minus f times del operator dot del operator, which is expanded into del operator times del operator dot f minus del operator squared times f. All right. Sorry, I should have scrolled down while I was explaining this, but that is what we're looking at as far as like curl, having that right there. And just I'm gonna center on this for a little bit just so you can see everything that I was able to flesh out. All right, on to Maxwell's equations. We're looking at the 4 foundational equations that I've put up here. Gauss's law for electricity, Gauss's law for magnetism, Faraday's law of induction, and the Ampere Maxwell law. In part A, we ask when the electric and magnetic fields are both incompressible, meaning they have 0 divergence. The magnetic field equation del dot B is equal to 0, so that means it is always incompressible by definition. For electric field, del dot E equals let me zoom in here so it is easier to see. Yeah, equals rho over epsilon, which is it equals electric charge density, which is rho, over epsilon, which is the permittivity of free space. For this to equal 0, the charge density rho must be 0. So notice, in part B, we look at when they're both incompressible and conservative, meaning there's 0 curl. And for the electric field curl, del times E, or cross product E equals negative partial derivative B over with respect to T to be 0. The magnetic field must be static, meaning unchanging with respect to time. For time, the magnetic field's curl to be 0, we need the vacuum of free current, also known as J, to equal 0, and a static electric field. So that brings us to, let me zoom out so that's visible. For part C, we are asked to, for part C, we're asked to verify that the specific wave function, specifically E equals 1 minus sine of x minus t for k, and B equals 1 plus sine of x minus t for j, satisfy Maxwell's equations in a vacuum where rho equals 0. The current density is equal to 0, and mu naught which is the permeability of free space, and how much a vacuum responds to a magnetic field, equals 0. Or sorry, equals epsilon, which also equals 1, which is the permittivity of free space and how easily an electric field permeates a vacuum. So yeah, when we plug these into the divergence equations, both evaluate to 0. When we test Faraday's and Ampere's laws, the curl of E matches the negative time derivative of B, and the curl of B matches the time derivative of E, proving they satisfy all 4 equations. And just to scroll to show a little bit more, because I put these on, I have a lot of pages and it was hard to fit all of these on. But yeah, now for the last portion, we're going to derive the speed of light. It's part D. Is the core of the project, deriving the wave equation, finding the speed of light. We assume a charge-free current-free vacuum, meaning rho equals 0, which is electron or charge density. J equals 0, and evaluate the double curl of del cross E equals del times del dot product of E minus del squared E times E, because rho equals 0. Divergence is 0, leaving us with only negative del squared times E. And that's for method 1 right here, if this is legible. For method 2, we substitute Maxwell's equation directly. We swap the inner curl for negative partial derivative of B with respect to t, pull out the time derivative, and substitute the Ampere-Maxwell law for del cross B. This yields mu naught times epsilon, negative mu naught times epsilon times the second partial derivative of E with respect to t, which we then set both methods equal to each other, and then that gives us the second partial derivative of E with respect to t is equal to 1 over mu naught times epsilon naught times del squared times E. Comparing this to the standard wave equation, we find out that here. Sorry, I lost my standard wave equation. It is actually down here. You get c squared equals 1 over mu naught times epsilon, meaning that the speed of light is equal to 1 over the square root of mu naught times epsilon naught. And then finally, we'll go to part E, or yeah, the final portion where you just verify the wave equation. So we'll simplify parameters where mu naught and epsilon naught and c all equal 1. So taking the second time derivative of our electric field function, E yields yields the sine of x minus t, which is k, taking a second spatial derivative via Laplacian, yields the exact same thing. Doing the same for the magnetic field function, B gives negative sine of x minus t on both sides, confirming that both fields successfully solve the wave equation. And I tried my best to kind of consolidate this video, but consolidating 10 minutes for 11 pages was a little difficult. But this project demonstrates well how multivariable vector calculus is like forms the mathematical structure for electromagnetism and wave propagation. So thank you for listening.